This talk discusses Align, a joint university industry project for generating open source software for analog layout generation. This project has been ongoing for a couple of years now. The motivation for the project is the proliferation of analog everywhere in applications from robotics to wireless infrastructure to high-speed networks, autonomous vehicles, and IoT applications. Although analog circuits form a relatively small part of an overall mixed signal chip, the amount of design effort required to build analog is disproportionate, as shown in this graphic. It's not just about the design effort, it's also about risk, because a large number of respin issues can be attributed to AMS issues. For that reason, automation is extremely important because it speeds up turnaround time and reduces design risk. Another way of looking at this is to see how analog design is typically carried out. If you have a circuit, it's typically optimized at the netlist level through topology selection and transistor sizing, making crude guesses at the parasitics. These are particularly crude when you go to very small technology nodes. And so what happens is that the netlist designer builds the circuit, passes it for manual layout to the layout engineer, and this is an intensive process that takes days or weeks. Then the parasitic guesses were probably all wrong, so it comes back for optimization, goes back to manual layout, and this cycle takes a really long time. Align's goal is to replace the green box by an automated solution that's fast and it's completed in minutes to hours. And by doing this, it enables faster iterations, a larger number of design iterations, and therefore leads to better performing circuits. The overall scheme for Align is as shown in this graphic. The input is an unannotated SPICE netlist. So the designer does not necessarily provide information on what is in the netlist, and we have to find and identify the blocks, annotate them in terms of their identity, in terms of symmetry constraints, hierarchies, etc. And that's done in the netlist auto annotation step. We also have to meet performance constraints, so we generate electrical constraints that the layout generator must meet in order to meet specs. We use the process design kit or PDK and abstract the design rules into a simpler form, and then start creating the generation of the layout. We start with the lowest levels of the hierarchy. These are blocks that we call primitives, and we build upwards from the primitives to higher level blocks until we come to the final layout, and we have a GDS for the entire layout. The Align layout generator is open source. The PDKs are obviously not open source for the most part, and so we have abstraction techniques that go from a proprietary PDK to something that could be used. The GitHub repo for Align is shown over here. The website is listed below, and version 1 was released in August or so. The project is going through continuous development, as you can see in the bottom right of this slide. The targets of Align are 4 classes of circuits: low frequency analog circuits, wireline, wireless, and power delivery. And each class of circuits has its own set of constraints and requirements. In fact, traditionally, it's been hard to build a unified analog layout generation tool because every circuit is different and has its own needs. For example, low frequency analog circuits require strong active and passive matching, but power delivery circuits may not require this. We color code the 4 types of circuits using red, blue, green, and brown, and we show how Align has been applied to circuits within each category as shown over here. We'll start with each specific block for Align, beginning with netlist auto annotation. Recall that the unannotated netlist has to be recognized, and we have to figure out what the blocks and symmetries in the netlist are. We use 2 approaches here. The first approach is machine learning based, and it applies to commonly encountered topologies such as operational transconductance amplifiers, or OTAs. OTAs, for example, are very widely used. There are a few hundred topologies that are available out there, and designers have their own variants. This is what makes analog design hard, but the core idea is that a human can look at it and recognize an OTA, And so a machine learning algorithm could do the same using approximate subgraph isomorphism. As an example, consider the netlist of a switch capacitor filter shown here. We represent this using a graph, and the GCN then performs approximate subgraph isomorphism to recognize nodes in the network that correspond to the OTA. So when we go down here, we see a set of red or brown nodes that are identified as OTA nodes, and the remainder are nodes outside the OTA. So now we can create a hierarchy associated with the OTA. We've applied this to other circuits such as a phased array, and we've identified blocks such as mixers, LNAs, oscillators, bandpass filters, etc. Although this technique is very appealing, one of its drawbacks is that it requires significant training. We need to supply a set of known topologies, the hundreds of variants of OTAs, etc. This is not really possible to do for a wide range of circuits. So approach B takes a different tack, and it says that if we look at a circuit and if we identify array structures in the layout, then these repeated structures are often placed together. They're often placed with symmetry, matching, or common centroid constraints. So we can design them once and replicate them. Examples are shown over here. In this circuit, you can see that the structure is repeated several times. And so we extract from it a capacitive array that's placed here. For the flash converter here, you can see that the comparator and resistor is repeated several times over here. And that again is an indicator of regularity. The R2R ladder shown here is again repeated. So we can recognize that and replicate it and place it using the required symmetries. And similarly, for a SAR ADC, you can see that these blocks are repeated. So by doing this, we auto-annotate the circuit and create hierarchies. Let's take an example of what we would do next. So the switch capacitor filter is shown here. Once we have the OTA, we have a smaller netlist to work with. And within this netlist, there are basic building blocks that are repeated in a number of contexts. So here you can see differential load, you can see a differential pair and current mirror. These are standard building blocks that we call primitives. And these are fixed structures, and therefore we have a library of such primitives, and we characterize these, we create a parameterizable cell generator for these, and we use these to build the overall layout. Now, as we are doing this, we also need to worry about constraints. Geometric constraints are constraints of symmetry, which could be within blocks. So for instance, if I look at this differential pair, there's a line of symmetry that says that these transistors should be on either side, and so on. There's also a larger line of symmetry over here for the OTA, and that is seen in the layout here. In a larger system where you have multiple blocks, the line of symmetry shown here has to be preserved through the entire layout. So you see the OTA over here, and then the switch capacitor network placed symmetrically over here. For further details, please look at talk 9B3 at ICCAD, where we present some of the algorithms that go below, that go into this, including machine learning approaches. In addition to geometric constraints, we also have to worry about electrical constraints. And the philosophy here is that we perform correct by construction synthesis of primitives, trying to stay close to the schematic. There are various degrees of freedom that we have in doing this. So for example, if you look over here, we can try to use multiple parallel wires to use resistive effects that degrade the GM of a device. Or we can change the aspect ratio, which also has an impact on the layout. And we use these to meet our constraints by trying to stay close to the schematic. At the block level, there may be constraints between blocks. So we have a methodology that constrains parasitics at sensitive nodes. More on that a little later. Next, we look at how we abstract the design rules from the PDK. Our philosophy is that we use a simple grid-based methodology. This is inspired by traditional lambda-based rules, but of course, those are not valid for 14 nanometer and below. And so we have a mix of kind of traditional grids and also another set of grids shown by dotted lines that correspond to stopping points on the grid. We place these objects so that we have limitations on the pitch, width, space, end-to-end, etc., that are captured within this grid. We may also have VR rules, and these VR rules could be Boolean. This leads to a simple abstraction that is massively simpler than the traditional design rule manual. We've applied this to a variety of commercial PDKs, FinFET, and bulk. We've applied this to synthetic PDKs, including the existing ASAP7, and we've generated mock PDKs based on data in the published literature for both FinFET and bulk processors. This has also been used internally within Intel. These are not synthetic PDKs. These are actual Intel PDKs going down to 3 nanometer process technologies. Mock FinFET PDK, which is available on our repo, is shown here. So this shows you, for example, metal layer M1 and various characteristics, the pitch, width, etc., associated with this. Similarly, for a fin at the device level, you can have design rules of this sort. Given these design rules, we now create layouts for individual primitives. These primitives are all parameterizable, which means that you can take the basic pattern and customize it for specifics. For instance, by layout pattern, it could be common centroid or interdigitated. You could change the size. It could be by changing the number of fins or fingers in a FinFET or the active width in a bulk process by changing the gate length. So over here, you can see a different gate length as compared to here. You can use a larger number of parallel wires as shown over here. This is for a FinFET technology. Again, in FinFETs, you could use a different number of stacked gates. So here, the blue lines, vertical lines are stacked gates. Here you have a single stack. Here you have 4 blue lines or a 4 stack, which is useful in various types of analog designs. We can also change the aspect ratio, which provides greater flexibility, both for performance and for layout. And this is shown for a couple of passive elements over here. We have a library of basic primitives that can be parameterized, and that library is listed over here. There are about 25 elements in there at the current moment, which cover a wide range of possibilities. For each of these, the layout is shown here, and the layout can be parameterized. We have recently even further improved the layout by using better diffusion sharing techniques. So this was the old layout. This is the much more compact new layout, which gives you a significant area and performance improvement. Moving on from there, once we've generated the layout for the primitive, the next step is to perform block assembly, placement, and routing. And over here, we start putting the blocks together hierarchically. So we perform macro placement using a simulated annealing engine. This engine has to be cognizant of constraints on symmetry, alignment, matching, etc. Then we go to routing. There's a global routing and a detailed routing step. Again, these have to be aware of symmetry, min length, the use of parallel wires to mitigate the resistive impact of wires, especially in lower levels of FinFET technologies, where the wires are very thin and very resistive. We also look at routing of supply nets in addition to signal nets. So we have a methodology that creates a top-level mesh, and that connects to lower-level blocks right up to primitives. A little more detail on this. The analog placer is based on a previously published simulated annealing sequence pair-based method. It supports symmetry, matching, and alignment constraints. The core placer does not handle performance, and therefore we need to use techniques that recognize good layouts and differentiate bad layouts to speed up simulated annealing and take it away from poorly performing layouts. So we have performance-driven placement styles that are based on machine learning models. The basic models were presented in this paper in ISVLSI this year. There's a paper in session 10B, talk number 2, on using graph neural networks. Please attend that if you can. And then there's an upcoming paper using support vector machines and multi-level perceptrons that will show up in ASPDAC 21. In terms of routing, we perform global routing using an integer linear programming-based formulation that supports symmetry. Detailed routing further adds matching, and it allows the use of parallel routes. So let's look at the results over here. This is a layout of a high-speed comparator. Signal routes are shown here. The power route shows the grid that's built over this and connections to the individual cells. Within the signal routes, you can see the use of parallel connections, which helps mitigate the impact of high resistance. In a FinFET technology, you have to use parallel routes rather than wider wires. For the power routing, you can see that in some cases where wire R is a significant constraint, you can have large IR drops. So again, you may use parallel connections to the power mesh. So let's try to put this all together using our old friend, the switch capacitor filter. And this is where we started. As we saw, we can recognize the OTA within here. After recognizing the OTA, we can break this up into primitives. And so this is really the annotation step. We've also recognized all symmetries within here. Now what we do is to take this and connect it to the design rules. So we abstract the PDK, and for each of these primitives, based on the sizes provided in the netlist, we generate a set of layouts for the primitives. These are our basic building blocks, and we build upwards from here and assemble these primitive layouts into an OTA layout with placement and routing. This gives you the layout of the OTA. Now we have to build the overall layout for the switched capacitor filter. So the OTA in this case is turned sideways. The line of symmetry is over here, which is the same as this line of symmetry. And the switched capacitor network is placed here symmetrically about the symmetry line. And the switches are here. The capacitors are the large objects that are shown here. We've applied this to other circuits too. This is the layout of an equalizer circuit. And again, you can see that it has a translation from the schematic to the netlist. The large blocks are the capacitors again. Other circuits include an optical receiver, as shown over here. This is a wireline circuit again. We have RF circuits. This is a bandpass filter, and you can see the large inductor, which is typical in an RF circuit. This is a data converter. It's a SAR ADC block, and you can see the capacitor array here and also the switches associated with this. Now, although the original intent of Align was to create no human in the loop flow, starting from the unannotated netlist to the output GDS, because Align is modular and because of designer interest, we also created multiple entry points into the flow. Entry point number 2 bypasses the netlist annotation and constraint generation and allows the user to provide these constraints. So only the modules that go beyond this are actually employed. Entry point 3 is a situation where the user also provides place and route guidance. And this was particularly useful for experienced designers. And then entry point 4 has a scenario where the user codifies placement and routing rules in Python. And then these are used to generate layout using the core Align tools. So as we go from 1 to 4, we are looking at a much more experienced designer. Designer number 4 knows exactly what he or she is doing, whereas designer number 1 really wants to treat this as a black box and generate a layout without worrying too much about what goes on inside. And there are good use cases for both of these. So to exercise this, we looked at some Intel designs, and this in particular is a strong arm comparator with kickback cancellation. With entry point 1, no human in the loop, and an offset spec of 5 millivolts, the spec was met using a layout that's shown over here. Then we provided entry point 2, where the designer provided some input, and we got this layout over here with a better offset. The first offset was also within specs. The area is a little larger. And then entry point 4 is kind of with intensive effort from the user. This also means that the turnaround time is a little larger. It's the order of a day to kind of put these constraints together. And this is the most compact, and it has a pretty good offset, though not as good as the second case. This is another example, an analog LDO from industry consisting of a compensation cap, error amp, and powertrain. The powertrain was built using entry point 4, and you can see that it's very compact and very regular. We've really generated layouts in 4 classes of circuits: low frequency analog, wireline, wireless, and power delivery. And recall that this has previously been hard for a single tool to do because of the vast difference in variety in the types of circuits that a layout generator has to handle. So all of these have been successfully generated. We've built these both in FinFET technologies and in bulk technologies. We invite you to explore this further. Please visit the Align GitHub repo. The website is shown over here. Play around with it. There are some examples that you can use. We also have more details in our upcoming paper in IEEE Design and Test. There are links from that paper to other papers that provide more details. The paper is currently in press and uploaded at archive. Thank you very much for attending this talk, and I look forward to interacting with you in future.